There is a material made by melting rock into a liquid and pouring it into a mold. It comes out harder than hardened steel. It does not corrode, it does not rust, and it does not care about salt, acid, or seawater. It has been manufactured in Europe since the late 19th century. It is still manufactured today, and there is almost certainly some of it inside a power station or a mine near you right now. And here's the honest part, stated up front, because that title asks a question, and I am going to answer it properly rather than leave it hanging. It was never banned. Nobody outlawed it, nobody suppressed it, and there is no buried patent. What actually happened is duller, and I think considerably more frustrating. The modern version of this material sits almost entirely outside the building codes, and a material that is not in the code is a material an engineer cannot specify, no matter how well it performs. That is not the same as illegal. In practice, for the application that matters most, it produces the same result. Let me start with the material itself, because the way it is made is genuinely strange. Basalt is the most common volcanic rock on the surface of this planet. It is what most of the ocean floor is made of. It is what the Deccan Traps and the Columbia River flows are made of. And there is an effectively unlimited supply of it in dozens of countries. Heat it to around 1300 degrees Celsius and it melts into a liquid, the way it was when it came out of a volcano in the first place. Then you pour it into a mold, and the interesting part begins. You do not simply let it cool, because rock that cools quickly forms a glass, and glass is brittle. Instead, it is cooled in a controlled way over hours, in an annealing oven, which allows fine crystals to grow through the material. What comes out is called cast basalt, and its properties are remarkable. It sits around 8 on the Mohs hardness scale, which puts it above hardened steel and just below sapphire. That scale is worth a sentence, since the numbers only mean something in comparison. A fingernail is around 2.5, ordinary glass is about 5.5. Hardened tool steel sits somewhere around 6 to 7. Quartz is 7, topaz is 8, and diamond is 10. So cast basalt is sitting in the same region as topaz, which is a gemstone, and comfortably above the steel it is replacing. That is why it survives abrasive slurry that eats through steel plate. The particles going down that chute are largely quartz sand, at 7, and a liner harder than the sand scratching it lasts an entirely different length of time than one that is softer. It is extraordinarily resistant to abrasion, which is the property that matters most in industry. It resists acids and alkalis. And it does not rust, because there is no iron metal in it to rust. It is already an oxide. It has, in a sense, already finished corroding several million years ago. So where do you find it? Inside the machinery of heavy industry, lining the surfaces that ordinary materials get destroyed by, coal chutes in power stations, ash handling systems, slurry pipelines in mining, cyclone liners, hoppers, launders, and the inside of pipes carrying abrasive material at speed. In those applications, a steel liner might last months. A cast basalt liner lasts years, and the arithmetic is straightforward enough that industry has used it continuously for over a century without any fuss. There are manufacturers in Central Europe who have been producing it since the industrial era began. And it remains an ordinary industrial product you can order today. The process is worth understanding, because the annealing step is the whole difference between a useful material and a pile of broken glass. Rock is quarried, crushed, and melted in a furnace. The melt is poured into molds in much the same way iron is cast, and at that stage what you have is essentially volcanic glass. Glass is brittle because its atoms are frozen in a disordered arrangement with no crystal structure to arrest a crack. Drop it, and the crack runs. So the castings go into an annealing oven, where they are held at high temperature and cooled slowly over many hours. During that slow cooling, fine crystals nucleate and grow throughout the material, seeded by the minerals already present in the rock. The result is not a glass. It is a fine-grained crystalline stone with the shape you cast, and those crystals are what give it its hardness and its resistance to wear. Get the cooling wrong, and the casting cracks in the oven or fails in service. Get it right, and you have a component that will outlast several steel replacements in the same duty. It is, in a real sense, a manufactured igneous rock. You have taken a volcanic process that normally happens over geological time in a lava flow and run it in a factory over an afternoon. So that is the first half of the story, and it is not controversial at all. Melted rock cast into shapes used where things wear out. The second half is where it gets interesting, and it starts with a different way of handling the same molten rock. Instead of pouring it into a mold, you draw it out through fine holes and spin it into a continuous fiber. Same rock, same melt, spun into a thread. That is basalt fiber, and it looks and behaves broadly like glass fiber, with one important difference. It is made from a single, naturally occurring, chemically consistent raw material with no additives. And it has better temperature resistance than ordinary glass fiber. An American patent for producing continuous basalt fiber was granted to Paul D.H. in Etoile-Sand. So this is not a recent idea either. The serious development happened in the Soviet Union from the 1960s onward. It was pursued largely for defense applications, and much of the research was not public. When the Soviet Union dissolved in 1991, that work became commercially available, which is why basalt fiber appears to arrive from nowhere in the 1990s, despite having a research history stretching back decades. There is a supply argument worth making here too, and it is unusual. Most engineered fibers require a manufactured feedstock. Carbon fiber is made from petroleum-derived precursors through an energy-intensive process, and it is expensive for that reason. Glass fiber requires a batch of several carefully proportioned raw materials, mixed and melted together. Basalt fiber requires basalt. That is the entire recipe. Quarry the rock, melt it, spin it. There are no additives, no binders in the melt, and no chemical processing beforehand, which means the feedstock is a single common rock available in enormous quantities across most of the world. That matters for two reasons. It means a country can, in principle, produce this material domestically rather than importing it, and it means the cost of the raw material is essentially the cost of quarrying stone. The energy to melt it is the real input, and it is genuinely significant, since you are holding rock above 1300 degrees, but compared with carbon fiber, the embodied energy is considerably lower. And compared with steel, you are not smelting or handling the associated processing at all. So the material has a genuine argument on supply and on footprint, quite separately from its performance, and that is part of why it keeps attracting attention. Now, why does any of this matter to you rather than to a mining engineer? Because of what basalt fiber can be made into, and because of the single largest maintenance problem in the built world, concrete is not strong in tension. It is superb in compression, meaning you can pile enormous weight on it, and it is weak when you try to pull it apart. So we put steel bars inside it because steel is excellent in tension, and the combination is reinforced concrete, which is the material most of the modern world is built from. It works beautifully, and it has one fatal flaw. Steel rusts. Concrete is alkaline when it is new, and that alkalinity protects the steel inside it by forming a passive layer on the surface of the bar. But over years, two things eat away at that protection. Carbon dioxide from the air slowly penetrates the concrete and reduces its alkalinity, a process called carbonation. And chloride ions, from dicing salt on roads or from seawater, penetrate the concrete and attack the passive layer directly. Once the protection is gone, the steel begins to corrode, and here's the part that destroys the structure. Rust occupies substantially more volume than the steel it came from. Estimates vary with conditions, but the expansion is large, and it happens inside a material that has nowhere to go. So the rusting bar swells and pushes outward, and it cracks the concrete from the inside. Those cracks let in more water, more oxygen, and more salt, which accelerates the corrosion, which produces more expansion, which produces more cracks. That is why you see concrete spalling off bridge soffits and car park decks with rusty bars showing through. It is not that the concrete failed, it is that the steel inside it grew. The cost of that, across roads, bridges, marine structures, and car parks, is enormous, and it is a permanent, recurring bill in every developed country on Earth. It is worth understanding how completely this dominates infrastructure maintenance, because most people assume concrete simply wears out. It does not. Concrete on its own is extraordinarily durable, which is why Roman structures with no steel in them are still standing after 2,000 years. What ages modern concrete is the steel we put inside it, and the clock starts the day it is poured. Chloride and carbon dioxide begin working inward immediately, and the depth of concrete over the bar, what engineers call the cover, is essentially a countdown timer. More cover buys more years. That is why bridge inspectors take cover meter readings and chloride samples, rather than simply looking at the surface. They are estimating how far the attack has penetrated and how long is left before the bars begin to go. And it is why dicing salt is so destructive to road structures. Every winter of salting drives chlorides deeper into the deck, and the damage is cumulative and irreversible. So a reinforcement material that is simply indifferent to all of that is not a marginal improvement. It removes the mechanism that sets the lifespan of the structure in the first place, which is exactly why engineers keep looking at it despite everything I am about to tell you about its drawbacks. Now put basalt fiber reinforcing bar next to that problem. It does not corrode. There is nothing in it to rust. Salt does not attack it, seawater does not attack it, and carbonation of the surrounding concrete does not matter to it because it was never relying on alkalinity for protection. It is roughly a quarter the weight of steel, which matters on site and in transport. It has high tensile strength, and by some measures, higher than mild steel by weight. It does not conduct electricity, which is genuinely useful around certain equipment, and it does not conduct heat the way steel does. So the obvious question is why every marine structure and every salted highway bridge is not built with it. And this is where I have to be honest with you, because there are real engineering reasons alongside the code problem, and I am not going to pretend the material is perfect. The first reason is stiffness, and it is the big one. Strength and stiffness are different properties. Strength is how much load a material can take before it breaks. Stiffness, which engineers call modulus of elasticity, is how much it stretches under load before it gets there. Basalt fiber bar is strong, and it is considerably less stiff than steel, roughly a quarter of the stiffness, depending on the product. That means a beam reinforced with it deflects more under load than the same beam reinforced with steel. The beam does not fail, but it sags visibly, and in a building or a bridge that is not acceptable. So designs using it are usually governed by deflection rather than strength, which means you need more bar, which erodes the cost advantage. The second reason is that it behaves differently at failure. Steel yields good stretches, it deforms visibly, and it gives warning before it lets go, which is enormously valuable in a structure because it means people can see a problem coming. Fiber-reinforced polymer bar does not yield. It behaves elastically right up to the point where it breaks, and then it breaks. Engineers call that brittle failure, and designing around it requires different safety factors and different thinking. The third reason is that you cannot bend it on site. Steel bar gets bent to shape by a man with a bending machine in the corner of the site, every day, on every job. Fiber bar has to be manufactured in its final shape at the factory because the resin is already cured. Every stirrup, every bend, every hook has to be ordered in advance and delivered correct. That is a genuine change to how a site works, and construction is an industry that does not absorb changes to how a site works quickly. The fourth reason is long-term data. Concrete structures are designed for 50, 75, or 100 years. Steel and concrete has over a century of field performance behind it, and we know precisely how it fails and when. Basalt bar has decades, not a century. There are questions engineers take seriously around long-term behavior under sustained load, and around the durability of the resin binding, the fibers in the alkaline environment inside concrete. Those are being studied, and the results are broadly encouraging, and they are not the same as 100 years of bridges. Now, the code, which is the answer to the question in the title. Building codes are not written to keep good materials out. They are written so that an engineer can put their name and their professional liability on a design and know that the material will behave as the calculations assume. For a material to be used structurally, there must be design provisions covering it, test standards, design equations, safety factors, durability requirements. Steel has all of that, developed over a century in every code in the world. Fiber-reinforced polymer bars have been working their way into that framework for years, and glass fiber bar is considerably further along than basalt. Guidance documents exist and are developing, but in most jurisdictions, for most structural applications, a designer cannot simply substitute basalt bar for steel and sign it off. Without code provisions and without an approval route, the engineer carries the risk personally, and no engineer does that on somebody else's project. So the material is not illegal. It is unspecifiable, which in practice means the same thing. And it is worth knowing that engineers already have other answers to the corrosion problem, which is part of why the pressure to adopt a new one is weaker than you would expect. Epoxy-coated steel bar has been used for decades, with a protective coating applied at the factory. It works when the coating is intact, and it fails where the coating is damaged in handling, which turned out to be a genuine problem in practice. Galvanized bar is another route, with a zinc layer sacrificing itself to protect the steel underneath. Stainless steel bar is the premium answer, and it works extremely well and costs a great deal. And a large share of the industry's effort has gone into the concrete itself rather than the bar, using denser mixes, supplementary, cementitious materials, and simply specifying more cover so that the chlorides take longer to arrive. Every one of those is an established, code-covered solution that an engineer can specify tomorrow. So a new material is not arriving into a vacuum. It is arriving into a field where several imperfect answers already exist, all of them approved, and it has to be better than those rather than merely better than plain steel. That raises the bar considerably, and it is a large part of why adoption is slow. And that is a genuinely frustrating answer, because it is nobody's fault and there is nobody to be angry at. The code exists to keep buildings standing. The material has not yet accumulated the evidence and the standards to get into it. Both of those things are reasonable, and the result is a material that outperforms steel on the single biggest failure mode in construction, sitting largely on the sidelines. Now, where is it actually being used? Because it is not, nowhere. Non-structural and secondary applications are where it has established itself. Concrete slabs on ground, pavements, and roadworks. Marine and coastal construction, where chloride attack is the dominant problem, and where the corrosion resistance genuinely pays. Repair and rehabilitation of existing structures. Temporary works, tunneling where soft-eye sections are deliberately built with fiberbar so that a tunnel boring machine can cut straight through them, which steel would not allow. That last one is a lovely example, because it is an application where the material's properties are not merely equivalent to steel, but are actively better for the job. And basalt fiber in general, separate from rebar, is genuinely established. It appears as chopped fiber in concrete, as fabric and mesh in composite panels, in insulation, and in a range of industrial applications where its heat resistance and chemical stability are valuable. So the picture is not a suppressed miracle. It is a material with real advantages, real limitations, and a slow, unglamorous march through the standards process. Now the honest comparison, because this video is called Better Than Steel, and I owe you a straight answer on that, it is better than steel at not corroding, comprehensively, permanently, and in exactly the environments that destroy reinforced concrete. It is better than steel on weight, on thermal conductivity, and on electrical conductivity for the applications where those matter. It is worse than steel on stiffness, which is the property that governs a great many designs. It is worse than steel on failure behavior because it gives no warning. It is worse than steel on site flexibility because it cannot be bent or cut and rebent. And it is worse than steel on evidence because steel has a century of it and this does not. So the honest verdict is that it is better than steel at some things, worse at others, and genuinely superior in a specific set of environments where corrosion is the dominant failure mode. That is a much smaller claim than the title makes, and it is the true one. Cast basalt, meanwhile, is not competing with steel at all. It is competing with wear plates and liners. It is winning that fight comfortably, and it has been winning it quietly for over a century. Now, the practical section, and here I have to disappoint anyone hoping for a build. You cannot make this at home. Melting basalt requires temperatures around 1300 degrees Celsius, held for hours, followed by controlled annealing, that is a furnace and an industrial process, not a garage project, and molten rock at that temperature is one of the more dangerous things in industry. So this is not a video about making something, it is a video about knowing something exists. What you can actually do with this knowledge is smaller and more useful than it sounds. If you are having concrete work done in a marine environment, a coastal property, a salt-treated driveway, or anywhere chlorides are a factor, ask your contractor and your engineer about fiber reinforcement options. For slabs on ground and non-structural work, it may well be available and appropriate where you are. If you are specifying anything structural, the answer will almost certainly be steel, and now you know why, which is worth something in itself. And if you own concrete that is already spalling with rusty bars showing through, you now know exactly what is happening. That is not the concrete failing. That is the steel inside it expanding. And the repair has to address the corrosion rather than simply patching the surface, or it will come back. Now, the limits and the cautions, briefly, because there are fewer here than in most topics. Cast basalt is brittle. It is extraordinarily hard, and it is not tough, meaning it resists abrasion superbly and it will crack under impact. That is why it is used as a liner, bonded into a steel shell rather than as a structural element on its own. Basalt fiber, like any fine fiber, produces dust when cut, and cutting fiber, reinforced products, requires respiratory protection and eye protection exactly as cutting glass fiber does. If you ever handle it, treat it with the same respect, and the material is only as good as the resin holding it together in a fiber bar. Which is why product quality and manufacturer standards matter more with composites than they do with steel, where a bar is a bar. Here's the thing worth keeping from all of it. More than a century ago, European industry worked out how to melt the most common rock on Earth and pour it into molds, producing a material harder than steel that cannot rust because it has already finished oxidizing. It went into the guts of heavy industry, and it stayed there, quietly outlasting steel in the places where things wear out. Without anyone outside those industries ever hearing about it, then somebody spun the same molten rock into fiber. And it turned out that the resulting material solves the single most expensive failure mode in the built environment, which is steel bars rusting inside concrete and cracking it apart from within. And it has spent decades working its way toward the codes. Slowly, one test program at a time. Because the system that keeps buildings standing quite reasonably wants evidence before it lets anything new hold up a bridge. Nobody banned it. Nobody hid it. It is simply that a material can be genuinely better in one crucial respect and still take 50 years to be allowed to prove it, and that is a far less satisfying story than a conspiracy. But it is the true one, and I think the fact that we can melt rock into thread and build with it is remarkable enough without needing a villain. Everything this channel has gathered on materials and methods that sit just outside ordinary use, with their real numbers and their real limits, lives in one place, linked right below. And the comments are where this one earns its keep. If you work in construction, in marine, or in materials, I want to know whether you have ever seen fiber bar specified on a real job and what the reaction was. My money is on it being a slab on ground and somebody asking why it was blue. As for the concrete the Romans made that is still standing after 2,000 years and heals its own cracks, that is on screen right now. Same problem, opposite century. Till next time.